Okay, so today's class will look at in bit more detail about what MAC layer does in 5G systems. So this is the outline for today's presentation. So we have seen in the previous class what MAC layer does. So we'll have a quick recap of what MAC does. Then we'll go look at how in 5G, how the downlink and uplink scheduling is done. So I will show you with a couple of illustrations how scheduling is indeed taking place, where the base station is the one which does the scheduling for both downlink and uplink case. Then I will talk about some of the classical scheduling algorithms that you may be familiar, like round robin, proportional fair, and other things. Then I will talk about various crusts of the scheduling algorithms because we don't have much time, so I won't be able to go deep into various classes of scheduling algorithm, but I will give you some reference material for you to go through and understand the rich set of literature that we have on the scheduling algorithm. Finally, we'll conclude looking at the interesting case of how MacLeod takes care of the reliability using something called hybrid ARQ with soft combining, which is very interesting concept, which is not there in most of the other systems that use like Wi-Fi and other. So I'll try to explain these in today's class. Let's see. Okay, so this is what I was talking about even in the previous class, where the MAC layer is the one which takes these RLC logical channels and multiplexes them onto transport channels, where the information on this transport channel is organized into something called transport block. Basically, at the end of the day, this is the one that is getting transmitted over the air, where the data of multiple users can be multiplexed onto one of the transport block by creating multiple subheaders and packing the things together, where these subheaders could contain the packets of different logical channels, which could either be part of the same user's traffic, or they could belong to different users' traffic. It's all up to the scheduler to decide which one to pack and how long to give the resources and all. And also it does something called priority handling between users by means of dynamic scheduling. If there are multiple logical channels for one of the users, it can also try to give priority to one of them by looking at the QoS flow identifier and other things. Okay. And also it has to inform the user that certain user data is coming to it in the downlink, so that user can start receiving it. That's what the scheduling information reporting. For this, it uses something called PDCCH, the physical downlink control channel, in which it sends something called downlink control information. And for error detection and correction, we use a hybrid ARQ. And if there is something left out, we use the padding here. Whereas we are not doing any padding at the RLC, there you are doing the segmentation. Unlike other layers that I talked about, SDAP, PDCP, RLC, the main difference here is the MAC layer is a single entity where it can support even multiple cells from given base station. That means we can create one base station which is serving 3 different cells at one cell site. And also using something called carrier aggregation, we can also support multiple transport blocks transmitted parallelly by the base station. These all comes under bit of the advanced, but for this particular class, assume that we have one base station covering or managing one cell. For that, we have one MAC entity. So this is what you might have remembered from the previous class. So here you see on the left-hand side how the multiplexing of different logical channel is happening at the U side. Then after multiplexing, we use hybrid ARQ to send the data over uplink shared channel. So uplink shared channel is the one that is common for all the users. It's not that one user can make use of the entire uplink shared channel. So which part of the uplink shared channel a given user can use will be conveyed to the user in PDCCH as part of downlink control information. So that is about the uplink, where the user is taking logical channels and multiplexing them into transport channels and sending it to the physical layer to send it over the time frequency resource grid. In addition to that, when you switch on your handset, it does something called a random access procedure. So that I will explain later. Is also being done in uplink by your handset. Look at what your handset does in downlink. That means when the base station is sending the data. Base station sends the data by doing scheduling in something called downlink shared channel. Again, this is also shared across multiple users. Let's say if the base station decides to serve two users in a given transport block, the data that is belonging to multiple logical channels of these two users are multiplexed into the downlink shared channel and send it over the air. Now, assume that this is the scenario at one of the users where the user is listening to the downlink shared channel. Then it feeds the data that is coming over the downlink shared channel into the hybrid ARQ reception. After that, it does the demultiplexing to feed the data into the appropriate logical channels. If it is the broadcast information or if it is the paging information coming from the base station, there are no hybrid ARQ and demultiplexing because they are meant for all the users. For that, we don't use a hybrid ARQ. Hybrid ARQ use only for user data, not for the broadcast or the control information. And I was
Sir,
also showing, oh, Suranjan, go ahead, yeah.
sir, you said that RATCH is because is there to for multiple access, right? So
Right?
carrier sense multiple access.
No, it uses something called slotted aloha.
Okay, so we are one side we are dividing the frequency and the time domain, and also using this.
Hmm. You are right. I will explain why we have to do that. So this is basically done in multiple cases. One of the case where you use this random access is when you switch on your handset. Handset could be very close to the base station or it could be very far away from the base station. In that case, we need something called timing advance. I think it is again a bit tricky to understand this concept. Hopefully, if I get time, I will explain in a separate class.
Okay.
And other case is when you want to send the data and the base station has not given you any resource for you to send the data in uplink, you will be telling to the base station that you want to send the data in uplink by sending your interest as part of the RATCH process. Yeah, you see it clearly. It is a slotted allow. Still, there is a chance of collision. That means when there are two users who wants to send the data in uplink, if they so happens to use same slot, and also there is something called preambles. If everything matches, there is still a collision. But this collision is not while you are sending the data. This is the collision for you to sending a request to the base station. That means we are kind of letting the multiple users try to contend for the medium where they can try to inform the base station about their willingness to transmit an uplink. Yes, still the collisions are possible, but they are only for a certain subset. We use something called patch at the physical layer. So we certain time slots or certain symbols in the physical layer is reserved for this random access procedure. Only there we use slotted alarm, where the rest of the physical layer, where we have these time frequency resource grid, they are done are kind of used based on the scheduling based. There is no chance of collision happening. Only in the extreme case, when there is no other option, we use slotted hello as part of something called RATCH. I will come back. It is especially relevant and important in the case of machine to machine or IoT traffic. And there are too many traffic and lots of work has been done how to reduce signaling overhead that you have to go through when there are too many devices and they try to do the RATCH process and all. I will come back later. So hold on for some more time, Suranjan.
Okay, sir.
And this is where I was showing you in the previous class also about how we do the multiplexing of multiple logical channels, where you take the data of multiple logical channels and you are adding subheaders. Here the subheaders are distributed, and also we see on the right hand side MAC control elements, which are the ones not coming from the RLC layer. These are the ones that are directly injected by the MAC layer. For example, if the MAC layer wanted to send any acknowledgements or negative acknowledgements, then it puts ACK or NAC as the separate MAC packet here or sub packet here and send it over there. And you see in the case of uplink, the MAC control elements are appearing on the extreme right. And if it is downlink, the MAC control elements appear on the left hand side. Where you see the subheader, we have the logical channel identifier where we can have 6 bits to distinguish between different logical channels that belongs to users. And so I think this is what I think I was showing you in the previous class as well. So let me directly go into this example. Okay, maybe before I'm talking about that. So any MAC scheduling that use, it needs to know what is the current channel condition at each and every user. That way it has to decide what should be the modulation and coding scheme to be used so that we can improve the effective reception rate of the packets. And also it has to know, at least for the uplink case, how much is the data pending at the user and what is the priorities of the different flows that are pending. And in the case of coordination of the multiple base stations, for the interference point of view, you want to know what are all the base stations that are interfering with this particular base station. So that way this base station can try to make sure that interference to the select user is minimized. To support this scheduling process, each handset transmits certain information to the base station. What it transmits, one is called channel state information. It is called CSI, which basically tells to the base station what is the current channel at each for the given user. That base station need to know. Accordingly, it can figure it out what should the MCS to be used. And also each handset has to tell to the base station what is the current buffer status. That basically the queue length. Buffer state is nothing but queue length for various queues that it is maintaining, and what is the remaining battery capacity at the handset. And also, if at all we are talking about MIMO, then it has to give additional information to support MIMO level processing by the base station. Let's look at the scheduling that is done both in downlink and uplink. Let's look at first the left-hand side illustration. So you should be able to appreciate what scheduling does by looking at these two pictures very closely. Look at what base station is doing at the top and what user equipment is doing at the bottom. If you look at very carefully, each user equipment is sending its downlink channel quality. Okay. So some of you may be getting doubt that how can user will be knowing what is the downlink channel quality. Can somebody try to answer how user can know what is the channel quality at itself?
SNR value or something like that?
Yes, you are right. SNR value or SINR value is what you are interested in telling to the base station. But how a user equipment get to know its SINR unless the base station has already transmitted something to it, isn't it?
Right, like the app that we are using was actually taking the data from the base station to tell us.
Yes. So to simplify the whole process, what the base station do is they use something called DMRS, that is called a demodulation reference signal in the case of downlink. And in the case of uplink, they do something called SRS, sounding reference signal. Basically, it is like a predetermined signal that is emitted by the base station periodically. And in the case of uplink, it is the sounding reference signal that is emitted by your handset at certain time intervals. So the purpose of these reference signal, as the name says, these are like a kind of a standard signal that base station knows, that user equipment knows. Let's say base station is telling something that you already know. So the idea behind that all this process is by looking at this DMRS that you receive, you know what is the one that base station has transmitted, and also you know what is the quality of the reception of the signal that you receive. By looking at the difference between these two, you can kind of estimate how good and how bad is the channel. If what the base station transmitted is what you expect the base station transmitting, it means that SNR is excellent. If not, you appropriately estimate what is the SNR and give that as the feedback to the base station. Similarly, in uplink, we use something called a sounding reference signal, which is again a standard signal that your handset and the base station know in advance. By looking at the quality of the reception of the SRS at the base station can know what is the uplink channel quality in this particular network. So that is the purpose of DMRS and SRS. They all come under what the physical layer does, but yeah, I'm not going too deep into what is being done at the physical layer, but at the high level, you can assume that it is something of a known pattern. By looking at the reception of that known signal, you can know how good or how bad is the channel, and accordingly you can inform the same to the base station as part of CSI. It is called channel state information. Now we have the packet scheduler running at the base station, and it got to know the channel quality at all different users. And also it knows the current status of the RLC buffer for various logical channels. Then what it does, now depending on what kind of scheduling algorithm that, for example, if you use round robin, yeah, you start taking out certain amount of the data from each of the RLC buffer and start creating the MAC packet with subheaders for each of the logical channel content and send it to the physical layer for coding and modulation. If it is some other scheduling algorithm, it will try to pick up some RLC buffer and multiplexes them before sending to the physical layer for modulation and coding. That's how it is done. But a very important point to make note of is all the scheduling decisions in downlink are done at the granularity of radio bearers. In other words, the scheduler can look at the content of each and every RLC buffer and can try to prioritize which one to be transmitted at any given scheduling interval. So that is the granularity that we do the scheduling in downlink. Look at what is happening in uplink. In the case of uplink, make a note that even though it is the users who want to send the data in uplink, who should be transmitting at what time is all controlled by the base station. That way, both the downlink scheduling and uplink scheduling are running inside the base station itself. Basically, it's like kind of remote control what we are doing at the base station in the context of uplink scheduling. So I was mentioning about SRS being used to estimate the channel quality in uplink, where it is not the user equipment which is estimating the channel quality. In this case, the base station itself is estimating the channel quality because SRS is the one that is transmitted by the user equipment. That way, channel quality information is readily available. No need of sending them as part of the CSI reports to the base station. Now look at what is happening. In addition to the SRS, your handset also may want to transmit the buffer status report and also the power headroom information. So that is also can be done. And now we have the uplink scheduler running at the base station. It could be independent of the downlink scheduler. For example, you can use round robin for downlink, and you can, let's say, use the proportional for uplink or something else. So it's all up to the operators, depending on what metric they wanted to prioritize. They can configure their uplink and downlink scheduling algorithms appropriately. Look at what is happening. The user equipment is giving the buffer status and the power headroom information. Already channel quality in the uplink is available at the base station. Based on these two, base station can decide who are the user who should be getting the scheduling grants in the upcoming scheduling interval. So then the scheduling information is conveyed as part of the PDCCH. That's what I was talking about. Physical downlink control channel, which carries something called DCI, downlink control information. This carries, the scheduling information is carried inside this. This channel is something that everybody is supposed to listen all the time. So that way all the handsets listen to PDCCH and comes to know whether the base station has given any signal for it to transmit in the upcoming scheduling interval or not. So they come to know that. Let's assume that UV1 is one of the user which is currently scheduled by the base station. That means received the scheduling grant to transmit in uplink. So then what the user one does is it has its own priority handling algorithm. So what it does as part of the priority handling is this is being shown here. Uh, User one gets to know how the channel resources are the number of resource blocks and what should be the MCS to be used to transmit. All that information is what conveyed by the base station. GNodeB conveys this as part of the scheduling grant or as part of the PDCCH. Once the handset receives the priority handling routine that is running at the handset, it is the one which actually decides which RLC buffer in content should be multiplexed to transmit in the uplink in the assigned resource blocks. In other words, the uplink scheduling is a kind of divided between the base station and the user equipment, where the base station decides which user should be served using what amount of the radio resources with what modulation and coding scheme. But the base station doesn't tell which logical channel data should be transmitted by the respective users in the uplink in the upcoming scheduling interval. That decision is completely left to the respective users to decide. So can somebody tell me why we kind of doing this kind of a distributed thing where base station is doing some activity and leaving the critical part of deciding which logical channel to multiplex to the handset? Can you guess why this kind of thing is done?
Sir, because radio resources are available at base station level, so it has the first right to decide which user should use which radio resource. But at the user level, some logical links will have higher priority. Like some will be like we did in that assignment. Some
Yes,
channels will be serving audio, some will be serving video. So audio has higher priority. So that is decided by user equipment.
you are right. But what I'm asking is why can't base station decide that?
Uh, I don't know, sir.
Base station may not be in the position to decide that which
Because,
is
yeah,
important to the UV at that point.
no, no. Why it is not in a position to decide that? Or in other words, do you think that base station has that information in the first place?
No, that's
That is the
that,
reason. It is as simple as that. Base station doesn't know the complete knowledge of RLC buffers and their relative priorities and other things. Do you know what the see? I was just mentioning about buffer status, right? Again, buffer status is not something where you give a fine granular detail about I have 10 buffers, this is the size of buffer 1, 2, 3, and all. It's not that. It tells whether it has any uplink data to transmit or not. So that way that the kind of feedback that each handset gives to the base station is a very coarse level, not fine granular level. It is all done to kind of reduce the signaling overhead. Otherwise, all the channel bandwidth will be consumed to talk about who should be transmitting and who should be receiving. We end up not having any resources available to actually transmit any user data. To address this problem, only a minimalistic amount of the information is conveyed by the respective user to the base station so that base station can take certain decision. Here we call it as selection of the transport format, which is nothing but deciding the MCS and transmit power and other things. Then you leave it to the respective users to decide out of the available RLC buffers, which buffer should be multiplexed to send the data in uplink. That way we kind of get the advantage of centralized scheduling and also reduce the overhead by giving some of the activity to the respective user equipments. So any questions or any other doubts that you guys having? So let me show you quickly how the scheduling is done in 4G in LTE in uplink. If you look at the figure, you should be clear that it is exactly the same at the high level or at the abstract level in 4G and 5G. So you see, there is not much change except in terms of the kind of control channel that are used and how they are multiplexed. At the high level, scheduling in downlink and uplink in 4G and 5G is the same. Where for the downlink, you do the scheduling at the granularity of radio bearers or the logical channels. In uplink, you do the thing at the granularity of the user equipment and let the user equipment to decide its course of action in terms of multiplexing different RLC buffers. Let me spend some time to talk about scheduling algorithms. And yeah, some of you might have already studied these scheduling algorithms as part of operating system earlier. Some things these things also are the same at the high level. The objective of the scheduling is the same. You have different requests that are coming and you have to decide which one should be serviced next, whether it is a downlink or uplink, assuming you have necessary information available for you to take these scheduling decisions. Like we have this classical round robin proportional pair, and another one is called maximum CQI or the maximum throughput. Here CQI stands for channel quality information. Basically, it is a channel quality information. So this is what I was mentioning about. We can use a DMRS or SRS to estimate CSI, or you can call it a channel quality information. Okay, and there are many there are many ways we can decide about the scheduling algorithms, and they perform quite differently depending on whether it is a full buffer case or whether it is a real user traffic scenario. So what I mean by full buffer is full buffer. It means here it assumes that the queue is not empty all the time. That means at each handset or at each user equipment, you always have one packet or other waiting in the queue, no matter at what speed you are serving the traffic. That is the meaning of full buffer. That is a kind of a loaded scenario. And other one is a real user traffic scenario. That means there is no, it may or may not be the case that all the time the queue is not empty. So, but to be able to really compare these algorithms, we can use these two scenarios where you can assume that, yes, I have infinite amount of the traffic to be scheduled or to be transmitted. Other cases, let's say I take voice over IP application or video streaming, or I take web browsing. In that case, sometimes your buffer could be in zero, sometimes they could be non-zero. And also we have different metrics to prioritize or to optimize for different users' point of view. And one of them is the complexity and scalability of the scheduling algorithms. So as the number of users increases or the channel bandwidth increases, your algorithm is becoming quite heavyweight, or it is simple enough so that there is not much overhead in actually deciding about who should be served. Other one is spectral efficiency. So spectral efficiency is the one that very often we start up to 4G, we kind of trying to prioritize or give importance to spectral efficiency. But as you go towards 5G, especially when you're talking about the millimeter wave, so spectral efficiency may not be the real objective or a metric to optimize or to improve. The reason being, especially here, when you go to these 24 gigahertz and other thing, we have more bandwidth than what you have been using last 100 years or so. So here, the objective is could be your energy efficiency, right? Because we are talking about millions of devices and where they want to transmit a lot of traffic. So there, you can have even entirely different metrics. And other metric that you also worry about is the fairness. When there are multiple users, whether you are being fair to all of them or certain users are facing any kind of starvation issues. Another one is the QoS provisioning. That's where you talk about prioritizing data of some users or some logical channels over others, depending on their relative priorities and preemption capabilities and other things that we discussed earlier. And you can even think of even other metrics, which could be a kind of a hybrid of some of these metrics or even other metrics, depending on the use case and application that you have in mind. At the high level, the system model for scheduling looks like this, where you can see on the left hand side, this is your base station. So it has the data of different users coming in downlink from internet. So you can assume that this is the data that is coming in. And this is the radio. And it wants to send the data by multiplexing over the radio. That is the thing. And look at on the right hand side, I have multiple users where each user, if you look at, they have also radios, and each user is also has this channel estimator to measure the channel state information. And where if the base station is transmitting some data, then it will be received by the transceiver, that is your radio unit, and it can give the feedback about the channel quality and whether it has successfully received the data or not to the base station in uplink, where you can use the physical uplink control channel. So like that, we can think of a system model using which we can give feedback to the base station. Then the packet scheduler running at the base station decides how to multiplex the data of different users. This is shown in the context of downlink, but similar thing we can even talk about even in uplink, where assuming that in addition to the feedback, each user equipment also provides its buffer status and other information to the base station. So let's look at how the packet scheduler looks like in the context of 4G and 5G. So if you look at the packet scheduler, it's get the QoS and buffer status information from higher layers. From the handset side, it using doing the estimation of DMRS, it computes the CQA information and gives that to the base station. That means finally it is given to the packet scheduler. Now it has all the data that is required for taking the scheduling decisions. One is the channel quality at each and every user, and what are all the QoS requirements of various flows which are currently part of different RLC buffers. Then look at what is done by the base station, that means the packet scheduler. It is doing two activities or two things, two decisions it is making. One is resource block allocation. Basically, let's say I'm not talking about what is resource block and all of that. I will come back to that in the following class. But at the high level, you can assume that these are the radio resources. Let's say we have 100 resource blocks. Like if you look at LTE with a 20 megahertz channel, we have something called 100 resource blocks. So it is up to the base station to decide how to share these 100 resource blocks that are available in the downlink across various users out there. It could be given to the single user or it could be shared across 100 different users. It's all the scheduling logic that is running inside the packet scheduler to decide. So that RB allocation map is nothing but which user is given what set of resource blocks in the downlink. That is the meaning of resource map or resource block allocation map. And for each of those scheduled users, what should be the modulation and coding scheme that you wanted to apply? That is done by something called adaptive modulation and coding block. This block, AMC, again, it stands for adaptive modulation and coding. Based on the channel quality information, it will decide what should be the MCS, that means what coding rate and what modulation scheme to apply for serving the respective user that are scheduled in the current scheduling interval or upcoming scheduling interval. So I'm showing you an interesting survey paper, even though it is a bit old. This was written in the context of LTE, but if you look at the most of the topics that I'm showing you as part of this course, they're equally valid for 4G and 5G. The following class, I will talk about the frame structure of 5G. That is the one that is quite different, or it is kind of a superset of what we have in 4G. But otherwise, what many of the layers that I was describing as part of the 5G are also there in 4G, except HDAP, that is what something specific to 5G. That is, if you look at this particular survey paper, it talks about various scheduling algorithms that one can think of. Again, these are not all these are not all of them are not specific to LT. These are some of them are classical scheduling algorithms, which are there all the way from GPRS onwards. But yeah, this paper is a good reference for you to go through and understand what is packet scheduling and what are all the different objectives when somebody is designing packet scheduling algorithms, how we can compare performance of these different scheduling algorithms in LT context. But the summary is more or less should be valid, and you can try to understand more by looking at this survey paper. So look at what is being done finally. The packet scheduler decided the RB allocation map and also found out what should be the MCS for the scheduled users. So that information is conveyed over the PDCH. To be more specific, PDCH contains something called downlink control information that actually carries. All the handsets listen to PDCH, that means they listen to what is being conveyed inside DCI and comes to know whether it has been allocated any resources in downlink. Then it will start decoding those resources, and how to decode all that is also conveyed because MCS is also given as part of the DCI. That way the handset has all the information that is required to be able to decode the data that is being transmitted by the base station. We
Sir,
also, oh,
just sir, are these resource blocks of the same size? Like if the QoS is higher for one particular application, then the base station will allocate more resource blocks to that particular
yes, that's what I'm
application.
saying. Right? You are right. So it is all up to the packet scheduling logic that you have in the base station.
Okay.
Yeah, ideally you want it to give more resources to the user that is having higher priority. For that, you are assuming that you have some QoS aware scheduling algorithm running at the base station. But if you are using round robin, even if you have someone with a high priority, it doesn't bother about it, isn't it?
Okay. Okay.
Okay, you are right. If there are 100 resource blocks out and there is one user who is supposed to be given more priority, you can decide to give, let's say, half of them to one such user, and the remaining 50 can distribute across all other users. Here, it's all up to how you decide the scheduling to run here.
Okay. Okay.
And we, in general, in wireless networks, the scheduling that you do is called something called channel dependent scheduling. So you can appreciate what I'm saying here by looking at this illustration. So look at this time versus channel quality for three different users. So don't ignore downlink and uplink, all that case. Let's look at this is the channel quality that is available for three different users. You see one dark curve, one light curve, and other one is one medium dark or medium light curve. User 1, user 2, and user 3. So the idea behind channel dependent scheduling is, so look at here, maybe I will show you here. During this time interval, out of these three users, if I ask you which user is having better channel quality, you say that it is the user 1. Am I right? Is that clear?
Is it because of the amplitude is higher?
Yeah, no, yeah. Look at y-axis. Y-axis is the channel quality. Yes, higher amplitude means better channel quality.
Oh, okay.
Yeah, you can like for example, you can assume it is your SNR. Okay. So let maybe I'll call it as t equal to 0. So at t equal to 0, again, I think we should not call it as t equal to 0 during this time interval. Okay, maybe I use 0, 1, 2. From t equal to 0 to t equal to 1. So you see that out of three users, the channel quality is better for user number 1, right? So what channel dependent scheduling does is, it always tries to serve the user who is having the best channel quality. So that is kind of reflected if you observe the curve, the illustration carefully. At time during the second interval, it has decided to serve user 3. then it is user 2, then it is user 3, then it is user 1. So that means at any given interval or during each scheduling interval, you look at what is the channel quality of all the users who have the data to be served. Then always you pick the one that is having the best channel quality. So it is also something called multi-user diversity. It is a very popular term in wireless communication. The idea behind multi-user diversity is when there are more users in the network, and due to various reasons, the channel quality of these users fluctuate with time, the way you see in this illustration for 3 users. But at any given time, as the number of users increases, you can always find some user who is experiencing better channel quality compared to all other users. By picking that user who is having the best channel quality, we can try to use the maximum or higher MCS. And by doing that, you are actually improving the spectral efficiency. Is that clear what I'm trying to say? That rather than serving the users in round robin fashion or by some other logic, by always trying to serve the users who is having the better channel quality and switching across the users at a smaller time scale. This time scale is many times in the order of microseconds or milliseconds. We can able to not only achieve better spectral efficiency, you can also ensure fairness, and also you can able to get maximum aggregate throughput in the system. That's what the channel dependent scheduling is about. So with more and more users, your ability to improve the spectral efficiency improves, because the probability of you getting one user with better channel quality improves as the number of users increases in the network. So this is the idea behind channel dependent scheduling. Let me talk about how different scheduling algorithms are comparable and how they do the scheduling, and whether they are aware of the channel quality or whether they are unaware of the channel quality. So first of them is the classical round robin that doesn't
I have a
require.
doubt in this side.
Ah,
Uh, so in this, does it mean that always the user with the highest channel quality will be served, or
yes, yeah, okay. If you are always serving the user with maximum channel quality or the best channel quality, that is called max CQI. There is a scheduling algorithm called maximum CQI that does exactly what you said. It always picks the user that is having the best channel quality. But what I'm trying to say is, by looking at the channel quality and picking the users who are experiencing maximum or higher channel quality, you end up improving the spectral efficiency. But again, it may not be the objective all the time for you. So if you look at the case where if there's one high priority user who is at the cell edge and who is experiencing always very bad channel quality, then you are actually doing the priority inversion. Even though he is the highest priority user, by not prioritizing during the scheduling time, you are facing the priority inversion problem, something you might have studied even in operating system. So that also may end up. So one has to be very careful in doing the channel dependent scheduling. Yes, you try to exploit this multi-user diversity, but at the same time mindful about what is the QoS requirement of various flows, and try to do some trade-off between these two. That means improving the spectral efficiency and ensuring fairness and solving the starvation problem for the users who are experiencing always bad channel quality. So
okay, understood.
let me come back. Let me go back. Okay, let me continue and talk about some of the classical scheduling algorithms and whether they have these properties or not. Hmm? But this is what is expected by most of the scheduling algorithms, because by this you're improving the spectral efficiency. If that is the one metric you wanted to improvise. Okay, the first one is the round robin, where you, let's say, if I go back the example of 100 resource blocks, so I can equally share among all the users that are there in the network. Or if you look at this previous example again, so here I serve user 1, here I serve user 2, user 3, then user 1, and I serve the user 2, then so on. That's what the round robin. So here, if you look here, the time intervals are not same, but in ideal case, in a typical case, what you do is like in a TDMA, like one third of the time, one third of the time. So that means what you are having is the time fairness. But even though you are giving one third of the time to one of the users, what if the user is having very low SNR or SNR? So if we actually look at the, let's assume that this user is having the medium SNR and this user having higher SNR. Yes, you are providing time fairness, but there is no throughput fairness here. If you look at the throughput, out of these three users, the user that is having the higher SNR will experience the best throughput. And the one with the lower SNR, the lowest SNR, will experience the least throughput. Yes, time fairness may not always translate into throughput fairness. So yeah, the classical one is the round robin, where you try to give equal amount of channel resources to the various users. But user with a bad channel quality end up having lower throughput. So there is no throughput fairness when you go for round robin. And it also leads to increase in the delay, and it is not suitable for real-time traffic. The second one that we talk about is the maximum CQA. I think somebody was already referring to this thing. Here, you always serve the user who is having the best channel quality. Because you are always serving the user with the best channel quality, it may also lead to starvation for other users. So especially for seller users or the users who are having high priority, but they're experiencing bad channel quality. Again, we can think of two kinds of algorithms here, which comes under channel aware algorithms. One is the maximum CQA and other one is the maximum throughput. We use these two terms interchangeably. We expect if you are having maximum CQI, you end up getting the maximum throughput, because once the CQI is higher, you'll be selecting the higher MCS. That will translate into higher throughput. So that we use these two terms, maximum CQA and maximum throughput, interchangeably. But again, as you see, it could lead to starvation and unfairness to the select user. So another algorithm that we can talk of, which is also comes under channel aware algorithm, is the proportional fair. Where the proportional fair is very suitable when it comes to non-real-time traffic. And it is the one that has properties in between the maximum CQA and round robin. So this is the most important. So if one can summarize what is proportional fair as it is an algorithm that is coming somewhere in between maximum CQA and round robin. So what does that mean? If you look at maximum CQA, it is trying to improve the spectral efficiency. And if you look at round robin, it is trying to improve the time fairness or the fairness among the users. But what you want is a scheduling algorithm that has the best of these two scheduling algorithms. That is the one that improves the spectral efficiency, at the same time avoids starvation problem for users with bad channel quality. So that can be achievable if you go with the proportional fair. As the name says, it is not completely fair. It tries to be fair to the extent possible. How it is doing this fairness and also trying to maximize the channel spectral efficiencies by using or by selecting the users by using this particular formula. Try to look at this equation. So at any given time, the proportional fair scheduling algorithm selects the user with relatively best radio link quality. How do you define the relatively best radio link quality? So look at the equation. Among the users, you calculate Ri over Ri bar. Basically, Ri here is the instantaneous rate of the user I, and Ri bar is the average rate of the user I. That means you not only measure based on the current channel quality, what is the expected data rate for the user I, you also keep track of over the last maybe 100 milliseconds or 1 second or whatever it is. What is the aggregate throughput or average, not aggregate, what is the average throughput each user is experiencing? If I have one user, let's say this is the base station, and let's say if I have the user A, and if I have another user B, and the user B is the one that will get better instantaneous rate, because this user B is the one that has better channel quality compared to user A, which is at the cell edge with a poor SNR. Because of that, what happens is initially the proportional pair tries to serve user B and try to avoid serving user A. But after a while, what happens? Can somebody think of, after a while, do you think that proportional pair picks user B or user A? And what parameter in this equation is helping in you deciding choosing the one of the users?
So the instantaneous data rate is what's guiding which one should be selected. So if after some time B is getting better data rate, then it will choose that one.
But B here, this example, B is not moving and A is not moving. On average, the channel quality at A is worse than channel quality at B. And assume that both A and user are having outstanding traffic all the time. That means it is a full buffer case. They wants to always transmit.
Okay. Then one may starve.
That's what happens when you look at maximum CQ or maximum throughput. But that is not supposed to happen when you look at proportional pair. So can you look at the equation very closely and tell me whether B will get starved or not? Sorry, whether A will get starved or not.
So the value of any user equipment, it is like the instantaneous rate divided by its own average rate, right, sir?
Right.
Yeah. So it would be like constant based on the previous values, right? So even if B is near the base station, B's average value also would have been in that range. So when we take this Ri by Ri bar, it might be in a similar range or so.
Actually, RI bar is the average data rate for user I. So over a time, when a channel will be starved or will not be getting, so this thing will decrease and it is inversely proportional to it. So the one which is starving will automatically generate a greater value by RI over RI bar if data is smaller. So after some time, the A will also be selected.
Oops. So I'm taking this example where I have one base station and this is user B and this is user A. So what we are looking at is the AI over AI bar. So initially I was saying that system, the scheduler, the proportional pair scheduler picks B, okay, and avoiding A. Because it is avoiding A, what happens to its AI bar? Sorry, what is that? Yeah. Here I could be the time instant, okay? So what happens to this value?
So it goes down.
Even though numerator is also low because its SNR is low, SNR is low. Because of that, the numerator is also low. But because you are not serving and is kind of getting starved, After it is not served for whatever the time interval on which you want to apply this logic, you see that the denominator is very, very close to 0. That way it will skyrocket no matter how good is the channel quality and whatnot with respect to user B. So that way system will pick user A even though he is at a disadvantaged location and ensure that there is no unfairness. Suranjan, is that clear? Ranjita?
Yes, sir. Okay, actually, I thought the denominator is average over all the users. That's why I
No, no,
thought
no,
that
no. It's
it
not
is
all the users.
constant.
Right? It is Ri bar is for user I for
Okay,
each of the. Hmm?
okay. And then we
Here,
are taking a maximum.
yeah, you always pick the maximum that. That way, the user A, who is having the least Ri bar, will end up having the maximum value of this particular equation or expression.
Okay, sir.
So that way we kind of ensure that each user will get certain average throughput or at least some minimum throughput for all the users. And again, what I'm giving you a high level overview of what is proportional fair. If you look at the literature, there are hundreds of proposals to further improve the performance of proportional fair. There are hundreds of algorithms which talks about even further amplifying how the proportional pair behaves depending on the relative priorities of the users using various parameters into the logic using which it selects which user to serve next. So let's look at a small example of how these three algorithms behave when there are two users. Here I am having two users, again time versus channel quality. One is blue, other one is red. These are the two users. The first one is maximum CQA or maximum throughput. Second one is the round robin. Third one is the proportional pair. First look at maximum throughput or maximum CQA. So here as you see, you always looking at user who is having the better radio quality. In this case, it would so happen that the blue user is the one that is having on average better channel quality. So it end up always serving that blue user. But round robin, it is so unfortunate that it has selected red user at the beginning, even though the blue user is the one having the better channel quality relatively for more amount of the time. But after that, it is selecting the red user. Oh, oops, opposite, right? In the case of round robin, it is selecting the red user first. After that, it is selecting the blue user. Ideally, if it is opposite, that means if it is selected blue user first and then it is selected the red user, would have got better performance in the round robin. But anyway, you always decide the thing based on the user ID or some other logic, right? That is the second case. Third case is the proportional pair, where you can see it is a kind of very quick to react to what is the aggregate throughput and what is the instantaneous throughput that user is getting. And accordingly, it is kind of selecting both the users. And if you look at the extreme right, look at this part. So if you look at maximum CQA and in the case of round robin, it has selected the blue user. But if you look at the proportional pair, even though it is the blue user who is having the better channel quality and can get a better throughput, it has selected and went with the red user, even though it is having poor channel quality, because it wants to set the user that is having the max of that Ri by Ri bar. So we can also look at how these algorithms compare with each other when you look at a full buffer scenario versus a typical web browsing. So full buffer is where we can able to deterministically say how these algorithms are comparable with each other. Because when you talk about web browsing or any other normal traffic, it all depends on whether the queue is becoming empty or non-empty. So that way their behavior could be different from what you expect when there is a full buffer or when they have non-empty buffer all the case. So it is the CDF, that is a cumulative distribution function of the user throughput. So again, It is the CDF of user throughput. That means if you have 100 users, at the end of the experiment, you just take the throughput of all the 100 users and you are plotting the CDF of those 100 users. Then the plot will look something like this if you take the full buffer scenario. What it is kind of saying that is maximum throughput or the maximum CQ is the one. It is always going with the user that is having the best channel condition. Because of that, most of the users are getting very poor throughput or almost zero throughput. So here it is a throughput 0 to or very high value. Then you have the round robin. Again, it is better than maximum CQI. If you look at in terms of the fairness, because it is not the case that all the users are having a very low user throughputs. Then we have proportional fair, which is even more fairer than even the round robin, because it is riding on the peaks of the different users by exploiting something called channel dependent scheduling that I was mentioning before I talked about these 3 classical algorithms. And if you look at web browsing, what happens as part of the web browsing is, yes, there could be a user who is having the better channel quality, but what if the user is not doing any browsing activity? In that case, you cannot serve that user. You have to pick other user, even though that user is having not so best channel quality. That's the reason why you see a slightly different way these algorithms are behaving. In this case, it's all depends on how you actually injected the web browsing traffic. Depending on the way you simulate your experiment, you can see these curves moving here and there. But in summary, you can see that proportional fair is the one that is performing in between round robin and maximum CQI. It has the best of both, and even you can say it has worst of both. Best of both means, yes, it tries to improve the aggregate throughput of the system. At the same time, it tries to also be fair to the users which are experiencing poor channel quality. So any comments? I think, okay, maybe I have a couple of more slides on the scheduling algorithm. So if you look at these scheduling algorithms in general, you can classify them based on the way you design this scheduling. One could be the channel unaware. If you look at the first one, that round robin, the round robin comes under channel unaware. And the second one is channel aware and QoS unaware. So can you tell me which of the 3 classical algorithms comes under the channel aware but QoS unaware case?
Maximum CQI.
Yes, maximum CQI, it is looking at the channel quality and picking the user. Yes, it comes under the second category of scheduling algorithms. And anything else? What about proportional fair?
The third one?
Why not proportional fair? Do you think where do you think proportional fair will fall among this classification?
So the third one.
So you are saying it is channel aware and QoS aware. Again, we are not, see, when we talk about QoS, I think you have seen, right, as part of the QoS flows and service data flows. There you try to talk about guaranteeing certain loss rate, throughput, and other thing. But here we are not really doing all that. Here, the object of the proportional fair that I described here is, it try to give, let's assume that if all the users are at equal distance and experiencing the same channel quality, then what happens to the proportional fair? How do you think it will behave, or how it will look like its performance if all the users are at same distance with the same channel quality? What happens to the proportional fair?
Round robin kind of.
Round robin.
Yes. And can you also say it is also equal to maximum throughput?
Yes.
Assuming that, yeah, you don't pick the same user even though all the users are having the same channel quality and the maximum throughput, right?
Yes, sir. Yes. Then third one won't be
Yeah.
that one.
Actually, it is the both proportional fair and maximum CQI or maximum throughput, they come under channel aware and QoS unaware. Whenever we say QoS aware, you have to bring the logical channel identifiers. That means we have to look at the RLC buffers and how you have set up these buffers. So unless you bring in this information, you don't call it as QoS aware algorithm. Okay. Then we have semi-persistent scheduling for voice over IP traffic. So if you are kind of giving the channel resources and changing that, let's say every 1 millisecond or so, there's a lot of signaling overhead incurred. Whereas voice over IP is something where you expect once the call is connected, you want to give certain constant amount of radio resources. For example, voice over IP, let's say it will take 18 kbps. So you want to give the channel resources that are equivalent to providing 18 kbps data rate throughout the call duration of the user. For that, it gives something called semi-persistent. It is not kind of a circuit switching, eh, but it is not like a packet switching. Semi-persistent is something that comes between circuit switching and packet switching. That you can use it for voice over IP or other kind of services that operators offer, where we expect continuous provisioning of radio resources. And if you want to bother about or worry about the energy consumption, then you can come up with energy aware resource allocation schemes as well. And finally, again, it's not the end of the classification, but one can also think of joint scheduling, or you can also call it as slice aware scheduling, where when you have these EMBB slice and ultra reliable low latency slice, how we can able to multiplex the users of these two slices and serve them. And I'm showing you a couple of recent papers which appeared in TON and other venues, which talk about how we can multiplex the users of these two kinds of slices and do this joint scheduling. So it'd be more complex, but that's how the scheduling research goes into. So we can have all this kind of classification, and maybe I will try to show you some of the things which are easier for you to understand. That is channel unaware. Again, the first one is the first in, first out. It's more like kind of a round robin kind of thing. Other one is called blind equal throughput. As the name says, it always looks after or kind of monitors what is the achieved throughput of each and every user. And it always try to make sure that the throughputs achieved by all the users in the system is exactly the same. That is called a blind equal throughput. So it is a kind of a throughput fairness. So this gives throughput fairness. And the first one is the one that kind of reduces the service time. Resource preemption is the one, as the name says, where you can try to give more priority to flows that is having some time sensitive traffic kind of thing. Weighted fair queuing is what's very popular in internet, where when you have various kind of traffic and I wanted to prioritize and other thing, where you can use weighted fair queuing with a drop tail queue and whatnot. Then it comes to the delays and latencies. Yeah, you can think of earliest deadline first, largest weighted delay first. Yeah, so these are kind of channel unaware strategies. Some of these terms that you might have studied in operating systems and other places where you have to decide among multiple users or multiple requests that are there. Same thing can be tried out here, but more advanced ones which are kind of factoring in the channel quality and all, you can look at in the survey paper. I think with this, I am done with the quick introduction to scheduling. Again, scheduling itself is a major topic. Again, in the interest of the time, we are not going too deep into the scheduling. But with this high-level information about how the MAC scheduler works in downlink and uplink, and how the classical scheduling algorithms are designed, depending on the application and depending on the metric that you wanted to optimize or improvise, you can think of various scheduling algorithms. As part of the project, we were kind of asking some of you to design new scheduling algorithms or even implement the existing scheduling algorithms which are there in the literature in a 5G NR module and compare how is the performance when you look at the full buffer case versus non-full buffer case. That means web browsing case. These are some of the projects that you can try out if you are interested in taking up those projects. So maybe in the next 15 minutes, I will try to conclude the chapter on MAC layer by talking about hybrid ARQ with soft combining. So in summary, hybrid ARQ is nothing but using both FEC and ARQ. I think all of you know what I mean by FAC. The forward error correction is the one that is used to correct the bit errors. So can somebody tell me the scenario where you might have heard about FEC and why FEC is used there versus using ARQ?
ARQ is more expensive in terms of time, and FEC is like I'm sending the data and correcting it in one go.
Sir, in the case of deep space networks, we don't have the we can't afford maximum transmissions. Like we can't transmit many times. So instead of that, we'll use a powerful error correcting mechanism so that we don't have to duplicate the data using ARQ.
So you are saying that for deep space where the propagation delays are so high, you
And
prefer
it's
using FEC or ARQ. You are right. Okay.
yes.
But is there any other place where on Earth did you hear about FEC? Other than deep space, uh, for terrestrial communication or in other scenarios, did you ever hear about FEC, forward error correction? All of you use hard drives, right? CDs, DVDs, Blu-ray disc.
Yes, sir.
All of them use FEC. Here, you cannot retransmit. You have to buy one more disc, isn't it? So that's the reason why we use FEC in all these permanent media. Along with the user data, not user data, along with the file information, you also store the FEC bits so that some of the bit errors can be corrected. And if it is like music or it is video, even if it is failing to correct some of the bit errors, you may not notice while the music or the video is kind of rendered. But if it is like regular files, when you are unable to decode successfully, then it is called file is getting corrupted. Then you lost the content of the file. So that's where we use these FEC, the forward error correction. Yes, we can also use it in the case of deep space networks. Hybrid ARQ is nothing but using the combination of FEC and ARQ. What does that mean? First, you try to correct the bit errors, okay, to the extent possible by avoiding the retransmissions. But in the extreme case where you are unable to correct because the channel is so bursty and lossy, then you end up asking the sender to retransmit it. That way, we are getting the advantage of both FEC and ARQ as part of the hybrid ARQ, which is the one that we use both in 4G and 5G systems. And also, we don't use the hybrid ARQ for all of the downlink channels or for all of the traffic channel that you out there. We use it hybrid ARQ only in the case of downlink shared channel and uplink shared channels, which carry the user data. The channel that carry like broadcast traffic and random access channel, there you don't use a hybrid ARQ. And hybrid ARQ with soft combining is even more powerful than hybrid ARQ. So it's not that we are doing only FEC and ARQ as part of hybrid ARQ with soft combining. As the name says, at the physical layer, we do something called combining, where you get data over multiple attempts, and even the unsuccessful data that was coming in the previous attempts is kept in the buffer, and you combine the data with the newly transmitted data, even though that is also got still some bit errors. You combine all of them nicely to be able to reconstruct with the assumption that over these multiple attempts, the different symbols got corrupted, and by combining all these data of multiple retransmissions, you end up having more symbols which are intact, and your ability to decode will improve, and your ability to check whether it is getting corrupted or not will reduce. I will explain what I mean by soft combining with a couple of illustrations later, but it is a very powerful concept which is done at the physical layer, even though hybrid hierarchy is done at MAC layer. And again, there's nothing called absolute reliability. Hybrid hierarchy also can fail even after soft combining, after ARQ and after FAC. In that case, the MAC layer discards the packet. Then it is up to the RLC layer if it is in AM mode to transmit. to retransmit if at all it is needed. And the hybrid HARQ that you use, we also call it as a HARQ. In both downlink and downlink, you use the HARQ in 5G. And unlike in 4G, in 5G, the HARQ is asynchronous and adaptive in both the downlink and uplink. Whereas in 4G, it is asynchronous in downlink and it is synchronous in uplink. What is the meaning of synchronous in uplink is when your handset is given certain data in downlink, the acknowledgement has to be sent by your handset in 3 milliseconds, exactly after 3 milliseconds after you receiving the data. You send either ACK or NAC. It is not ACL, it is ACK, yeah, not ACL. Okay. What is asynchronous means? But again, in 5G, it is asynchronous. What is the meaning of asynchronous is in both downlink and uplink, the ACKs and NACs can be transmitted at any time. That way, the 3 millisecond time limit, which is not acceptable for real-time traffic or ultra-reliable low latency application, is avoided in 5G by also using asynchronous HARQ in uplink. And we say HARQ is adaptive. What is the meaning of that? Depending on the channel conditions, you decide what should be the MCAs and how many FEC bits that you wanted to set. And depending on the packet size, you set whether it should be CRC16 or CRC24. So all of them are kind of highly configurable and adapted based on the channel conditions. So let's look at this illustration, which is kind of showing the ARQ. That means a retransmission part, where we use the 16 stop and wait processes in 5G, whereas it was 8 in the case of 4G. But this illustration is with 4 stop and wait processes. So look at the illustration. What you see is we have transport blocks. So you can assume that transport block is nothing but your MAC packet. So if you recall, oops. This is your MAC packet. I was showing about MAC packet with distributed headers. So yeah, that is coming as a transport block to the physical layer. Look at what physical layer is doing. The physical layer takes, or the file layer takes each of the transport block and sending it using 4 different stop and wait processes here. So look at what happened here. So let's assume that this could be at the base station side. And this is at the user equipment side. And this is over the air, okay? The first one is received by process 0 and it has been successfully decoded. Oops. And there is no error. So it is demultiplexed successfully. Whereas the second one has been transmitted by the base station and the user equipment has received it over process 1. That means stop and wait protocol instance 1. But in this case, CRC has failed. So because of that, it has sent a negative acknowledgement. And the third one, yes, went successfully. Where is that third one? Yeah, third one is here, yes. Okay. Fourth one. So as you see clearly, the 1, 3, 4 and 5 were received before second packet. In other words, second transport block has been successfully retransmitted. Yes, it has transmitted and it received NAC and it has again retransmitted. That's what you are seeing it here. Ideally, you should be like, you receive the NAC first, based on that again you retransmit. And now it has, oops, okay. Where is that? Retransmitted. Oops, okay. It should be like this, yes. Yeah, it received NAC and it has retransmitted the second packet again at this time and processed and successfully received, and it has sent to the higher layer. So you can see 1, 3, 4, and 5 were demultiplexed and transmitted to the higher layer even before it received packet 2 successfully. So the reason why we are using multiple stop and wait processes, if you are using only one stop and wait, you are not actually using all the channel resources. Where each packet, if you look at each transport block, you can assume that it is sent over interval of 1 millisecond. I have sent this over 1 millisecond, and the acknowledgement will take certain amount of the time to come back. But you don't want to waste the radio resources for you to get ACK or NAC from the receiver. The way you can speed up the thing is setting up either flow, what is that, sliding window protocol. But in this case, what has been done is rather than using sliding window, they have decided to use 16 stop and wait processes, where you can able to send 16 of them in parallel, where you can take different transport block and put them over one of them. And if at all you need in-sequence delivery, again, that can be configured at the PTCP layer. Let's look at another example. Again, I'm showing you the HARQ part only, where if the CRC fails, the receiver will ask sender to retransmit. This is also the same similar example with the 4 processes running between the sender and receiver. It could be the base station and the user equipment, and vice versa. So what you can look at, what you can say from this example? Can somebody tell me what you notice in this example compared to the previous example?
Here we are just showing it differently, but it's essentially the same thing. Basically, different processes are sending some blocks, and if they are getting NFC, then it is again resending it.
Okay, where do you see NAC here? You see NAC here for block 3,
Yes, yes, yes. That one, and
and you
in
can see it for block 7.
yes, in process 2 as well for block 6.
Yes, block 6, yeah. So that way you can see the out of order reception of these blocks at the receiver. Okay.
Right, right.
And we have also another interesting concept, which is also related to ARQ. So far, I'm talking about at the transport block level. But sometimes this transport block can carry even millions of bits. What is the meaning of that? When I'm having a transport block of size, let's say 10 MB, let's call it as it is size is 10 megabyte. And if my CRC fails, that's what the ARQ mechanism checks. After receiving the MAC packet, you check whether the CRC is success or failure. So in general, what happens is the MAC layer creates the transport blocks and give to the file layer. What the file layer does is it takes the same transport block and adds the CRC. So that's what it does. But again, I'm talking about adding a CRC check, in this case CRC 24, to 10 megabyte MAC packet. And if it is failing, that means if the CRC check is failed, then what I have to do, I have to retransmit entire 10 megabyte. But it may not be the case that all 10 megabytes were actually got corrupted over the transmission. Maybe 10 bits out of 10 megabytes got actually corrupted. So then what could be done to reduce the overhead of retransmitting entire 10 megabyte? What one can think
We
of?
can we can add more CRCs. Like, let's say we break the 10 MB into 1 MB slices, and then we add 10 such CRCs. Maybe we can pinpoint where exactly the error was.
Exactly. Yeah, something like that we do. Yeah, you're right, Suranjan. So that's what I'm showing here. We do something called a code block. Uh, so, oops, this is the transport block, okay, with CRC. Yes, assume that already this has CRC inside it. Okay. So what we do is, as part of this code block group level retransmissions, first we take transport block and you divide that into multiple code blocks. Like each code block size could be, in one of the case it is 84, I think 24 bytes, 24 bits, the size of each of this block. And to further reduce the overhead, what I'm showing here is the code blocks are actually grouped further into, like in this example, if you look at, I have one transport block, which is divided into 6 code blocks. The way we can do is I can transmit the transport block as a collection of 6 code block, where each of them has its own CRC. At the receiver, you check the CRC and you came to know that the CRC for third code block is corrupt, is failed. Then what happens? We can inform this particular thing to the sender. Sender will retransmit the CB3 again. But in practice, what happens is we may having even thousands of code blocks in the transmission. Thousands of code blocks. There's a lot of overhead in actually pinpointing one specific code block that actually got corrupted. To further reduce the signaling overhead, what has been done in 5G is the code block have been further aggregated into something called code block groups. This example I am showing where 2 code blocks are combined together to form one code block group. In this case, even though only the third code block is actually failed, code block 3 and 4 will get retransmitted, because the feedback that you are giving from receiver to the sender is at the granularity of the code block group, not at the granularity of code block. It is basically done to reduce the signaling overhead, even though it is actually leading to more redundant transmission of one successfully transmitted code block. So that is the thing. And right hand side, you see how this transport block is mapped into time and frequency grid. So you can assume this could be your time axis. So this is your frequency axis. And assume that this is the entire thing is your transport block. Out of that, one of the code block or couple of code blocks that got corrupted. So by identifying the corresponding code block groups, you can give the selective negative acknowledgement to the sender, and we can retransmit only that, so that we can avoid retransmitting the successfully transmitted part, and can significantly cut down on the amount of radio resources that are used for retransmission of unsuccessfully received code blocks. Maybe I will stop it here. Already we are at 4 o'clock. So there is also a couple of other concepts that are out there. I think you can see how we can use the code block to convey between sender and receiver, in this case user equipment and the base station. And we have something called FEC and soft combining. So far I was talking about only about ARQ. So maybe in the next class I will quickly conclude how we do FEC in 5G and how we further do soft combining on top of ARQ and FEC to be able to significantly cut down the retransmissions and able to make sense of partially successfully received data to improve the spectral efficiency further. This I'll come back and discuss in the following class. So let me stop it here. If somebody is having doubts on the 3 things, one is how scheduling is done in downlink and uplink by the base station itself. Second one is about introduction to classical scheduling algorithms and classification of the scheduling algorithm. Finally, about hybrid ARQ, where we looked at ARQ part, where we can further look at optimizing the ARQ overhead or reducing the ARQ overhead by grouping them into something called code blocks and code block groups.
Sir, I have one doubt, like it is way back in DMRS and SRS part. So is it something like the beacon frame of Wi-Fi, like 802.11?
No. Beacon frame of Wi-Fi, we have some like the equivalent of beacon frame. Beacons in Wi-Fi is equal to, I don't know whether you remember or not. I was talking about something called master information block and system information block as part of the broadcast channel and downlink shared channel. If you recall, so those are the channels which actually carry information that is typical to what beacon frames carry in Wi-Fi, where they advertise about what is the channel bandwidth and downlink and uplink, what is the operator's country code, what is the operator's network code and whatnot. But these reference signals are something which are very specific to cellular networks. They are there all the way from 2G systems. Like even in GSM, we use something we call it as something called training bits. So whenever you are in a voice call on 2G networks, not only you send the voice bits of the user, you also send certain training bits, which are like some predetermined bit pattern that is known between the base station and user equipment. The idea behind sending the training bit is exactly similar to the reference signal that I talked about, where base station, when your user equipment is sending voice bits along with the training bits, it already knows that from certain location to certain location, it is expecting the training bits, and it also knows what is the training bit pattern at the base station. By comparing what it has received versus what it is already having, the difference between them will actually help the base station to appropriately configure the physical layer parameters, all the demodulation related. It all comes under the wireless communication, so which is not part of this course, or if you are interested in, you should look at into the physical layer. If you recall, I'm not discussing much into the physical layer because physical layer is something that comes under wireless communication, but yeah, that's where the things become more complex and will be taken care in entirely different fashion.
Oh, okay, sir. Okay, sir.
So I will share some material. Yeah, you can go through, but again, that is not the scope of this course. Yeah, we'll stop at the MAC layer because layer 2 is what we look at the networking level or the system level. Layer 1 is like comes under wireless communication. But having said that, the next class, again, as I was mentioning now, so if you look at here, so far we are at this location about adding the CRC check. Then we have the coding, that is the channel coding, where you use the turbo codes or LDPC codes in 4G and 5G respectively. Then we do something called rate matching. Then we do something called punching the code words to further reduce the parity overhead when you're transmitting the data for FSC part. Then you do the modulation. Actually, all these things, the one you see it here, actually these are the physical layer processing. But it is important to understand at the high level what physical layer does to look at the flow of how the packets start from HDAP layer, go to the PDCP layer, comes to RLC layer, comes to the MAC layer. Finally, they end up going to the physical layer where they further added with the CRC. Then you can also do the code block level segmentation. Then you do the code block level grouping. Then you do the channel coding. Then you do something called rate matching. I will come back and discuss. But yeah, this is a bit involved to understand all this as part of this course. But I'll try to explain a bit more in the following class. What we are doing it here as part of hybrid HARQ, which also involves going to some extent what physical layer is also doing, unfortunately or fortunately.
Okay, sir.
Okay.